Vector-valued functions. Objectives. By the end of this lesson, you should be able to define and graph a vector, explain horizontal and vertical components of a vector-valued function, find derivatives of vector-valued functions, and solve applications involving position, velocity, and acceleration vectors, as well as applications involving speed, displacement, and distance. We'll start by defining a vector and terms related to vectors. So a vector is a quantity with a magnitude or a size and a direction. So the notation for a vector is given by either a lowercase letter with a little ray above it, and the ray is always facing to the right, or we have a bolded lowercase letter. And a vector's representation, as far as graphically, is a directed line segment, or a ray, where the length of that ray, that vector, is the magnitude, or length, or norm. So these are all synonymous ways of saying how long that ray is. And the notation for the magnitude is given by what looks like these absolute value bars around the vector. So in general, when I'm talking about a vector, what I want you to think about is a ray. So a ray, thinking back to geometry, looks like an arrow. So this would be my vector u, and the length of the vector has a special name. So either the magnitude or the norm, or just the length of the vector. So how long I decided to draw that particular ray. So this here would be considered the norm, or the magnitude. And then the direction the arrow points in is the other piece of the definition of a vector. So it has a magnitude, or a size, or a length, how long the arrow is, and a direction. So typically, we want vectors to have an initial point at the origin. So right now, this vector that I drew sort of just hanging out in the middle of nowhere. We want to put this on an xy plane and have the initial point, so the initial point being the one that doesn't have the arrow at the end of it. So this it would be my initial point. And then the terminal point would lie at a coordinate point on the xy plane. So the tip of the arrow that we drew, the tip of the ray, that would be considered the terminal point. And that's going to end on an xy point on the xy plane. So when this happens, when we have a vector with its initial point at the origin at 0, 0, then we write that vector in these brackets, or alternatively we can write them in parentheses, but it's typical to write them in brackets just so we could distinguish between a vector and a point. And then the magnitude of that vector, if it has an initial point at the origin, has a nice formula. The length of that vector is the square root of x squared plus y squared. So let's actually draw what I'm talking about here. So if this time I have an xy plane, and I have my vector starting at the origin and going any direction from the origin I want. So I'll just draw it in the same way I drew this one. So here's my vector, and it can still be represented by a lowercase letter with a little arrow above it, but because now this terminal point lands on some coordinate point, x comma y, and it's, oops, that's a point, so I want to put it in parentheses, and this one started at 0, 0, now I can say that this vector can be represented by bracket x comma y, and then the length or the norm or the magnitude of this particular vector can be found. So remember, the absolute value bars around a vector don't just mean make the quantities positive, it means find the length. So the length is given by x squared plus y squared, which is really just the distance formula between these 2 points, between 0, 0 and x, y. So you will see, depending on the worksheets or the books or any videos that you may watch on vectors, you will see this notation being used interchangeably at times, so the brackets and the parentheses, but I'm going to use the brackets because I really think it distinguishes between the coordinate points and the vector, the actual ray that we're talking about. And then we call x the horizontal component and y the vertical component. So hopefully that sort of makes sense because x values move across the horizontal axis. So here the x quantity of the actual vector is considered the horizontal component, and then the y quantity is the vertical component. So because the y-axis is the one that goes up and down. In this first example, I want to graph the vector u, which is given by -3, 4 inside of these brackets, which means that my initial point is going to start at the origin, and my terminal point is going to end at the points on the xy plane, -3, 4. And after we graph it, we want to find the magnitude. So the absolute value bars around a vector means how long is it? What is its length? What is its norm? So here, let's go ahead and draw an xy plane. And what we know about our vector is that it's going to start at 0, 0 because this vector is in these brackets. And it's going to end, the tip of the ray is going to be at the point -3, 4. So -3, meaning I go left, so I'm just plotting regular Cartesian points. So -3, and then I'm going to go up 4. So right here, that's going to be where my tip of my arrow lies. So I'm starting here at 0, 0, and then my ray, the tip of my little arrow, is going to end at the coordinate point -3, 4. But this actual ray is the vector u, or bracket -3, 4. So now I'm interested in finding how long this particular ray is, so the length, the norm, the magnitude. So the formula for this, so for the magnitude of u, it's going to be the square root of x squared. So the x component, the horizontal component, is -3. So -3 squared plus the vertical component, the y value, squared, all underneath the radical. So this is square root of 9 plus 16, which is the square root of 25, which is +5. So that means the length of this vector is 5. And so hopefully you can see this is the distance formula. So the distance formula in general is x2 minus x1 squared plus y2 minus y1 squared. So here our x1, y1 and x2, y2 correspond to my initial point, which is 0, 0, and then my terminal point, which is -3, 4. So that's where this formula is coming from. It's the length of this line segment. Now that we've defined a vector, we're going to extend that definition to talk about a vector-valued function. So a vector-valued function is of the form u of t, so u has the vector notation attached to it, equals x of t, y of t. So this is inside of those brackets, meaning that we're discussing vectors still. And x of t is the horizontal component, and y of t is the vertical component. And both of those are defined as functions of the parameter t. So our application of vector-valued functions is going to go back to a topic that we've covered in the past that relates to position, velocity, and acceleration. So we're going to have position, velocity, acceleration vector-valued functions. And then with the notion of velocity, we can talk about the idea of speed. So the position vector-valued function, well, position means where is my particular object at. So S of t is x of t, y of t. So where is my horizontal component, and then where is my vertical component at this parameter, or at this time t, because now we're talking about the position, velocity, and acceleration of an object in real time. So S of t equals x of t, y of t is the position of the object at any time t. And then how do we go from position to velocity? We take the derivative. So the nice thing is we can take the derivative of each component individually. So each component is its own function of t. So we take the derivative x prime of t, y prime of t. And that is the velocity of the object at any time t. So we're going to break it down a little further. We're going to take a look at, well, what does x prime of t mean? X prime of t, well, that's dx dt. That's the rate at which the x-coordinate is changing with respect to time t, or it's the velocity of the object in the horizontal direction. And then y prime of t, well, that's dy dt, that's the rate at which the y-coordinate is changing with respect to time t, or it's the velocity of the object in the vertical direction. So now we're breaking up to look at the horizontal component and the vertical component separately, and we're thinking about the rate of change of each one. So how fast is my object moving to the right or left, or how fast is my object moving up or down? So we're really sort of decomposing and getting more in depth with the rate of change concept. And so how do we go from velocity to acceleration? We take the second derivative. So we take the derivative of the first derivative and each individually, so x double prime of t, y double prime of t. So that's the acceleration of the object at any time t. So now, how do we involve speed in this? Well, speed is the absolute value of velocity, but velocity is a vector. So if I put these absolute value bars around this velocity vector, the absolute value bars mean magnitude or length or norm. So the formula for the magnitude, remember, was the square root of the horizontal component squared plus the vertical component squared. Well, my velocity vector, my components are derivatives. So x prime of t, that's dx dt, and y prime of t, that's dy dt. So we're squaring each of those, adding them together, and it's the square root of that sum. And so here's an alternative way of looking at it. So dx dt is x prime of t, and dy dt is y prime of t. So to find the speed, we need the absolute value of velocity. That's true, but when velocity is a vector, now we need the magnitude or the norm of that vector to find the speed at a particular time. And now we need to look at the formulas for displacement, position, and distance traveled before we do some examples. So we're going to suppose an object moves along a path in the plane so that its velocity at any time t is given by v of t equals x prime of t, y prime of t. So we have this vector-valued velocity function. To find displacement of that object from time a to time b, it's given by the vector. So we have the integral from a to b of x prime of t dt plus the integral from a to b of y prime of t dt. So we can think about this as its own separate formula that we have to memorize, but hopefully we remember the formula for displacement when just given a velocity function, not a vector-valued velocity function. Displacement was found by the integral from a to b of just v of t dt. So that was how we found displacement in general with just a velocity function. So hopefully you can see, well, now I'm given a vector value velocity function which has two components, x prime of t, y prime of t. So if I need to find the displacement, I need to integrate each component separately. So that's where this formula is coming from, the integral from a to b of x prime of t and the integral from a to b of y prime of t, each is their own component in a vector. And so now, to find the position at time b, so at the ending time, well, I needed to know where I was at the beginning. So I needed to know my initial location or my starting point. That's what this first vector represents, is my starting point. So to find my final position, I needed to know where I started plus my net change in position, which is displacement. So that is, again, a review concept. So displacement is my net change in position. So we have my starting point plus my displacement. If I add those two together, then I'll figure out my position at my ending time, my time b. And so finally, to find distance from a to b, that's going to turn out to be arc length. And the reason is because, so again, let's think back to our distance integral when I just had a velocity function. So distance was the integral from a to b of the absolute value of velocity. Well, we're talking about a velocity vector, so absolute value turns into the square root of x prime of t squared plus y prime of t squared, because remember, now that's the norm. So I'm integrating the norm, so that ends up being the arc length formula. So the length of the curve, so we're talking about an object that moves along a parametrically defined curve, which is ultimately what this is, because I have a horizontal component and I have a vertical component. That's going to end up being just the arc length formula. So again, it's not something that we should really take the time to memorize if it's completely different. If I remember that distance is the integral from a to b of the absolute value of velocity, and I remember that absolute value in terms of vectors really means the norm. Now I'm just applying that concept to replace the integrand, and then from there I can solve. Let's start with our first example. A particle moves in the xy plane so that at any time t where t is greater than or equal to 0, the position of the particle is given by x of t equals t cubed plus 4t squared, and y of t equals t to the fourth minus t cubed. And we're asked to find three things: the velocity vector at t equals 1, the speed of the particle at t equals 1, and the acceleration vector at t equals 1. So here we're given information about the position of the particle. So we're given each of the horizontal component functions and the vertical component function. So although it wasn't written out for me like this, I was given s of t as my vector value position function. So s of t is t cubed plus 4t squared, and then t to the fourth minus t cubed. So I can think about the information given as being given the actual position vector valued function. So for part A, I'm asked to get to the velocity vector. So that means I'm going to take the derivative of each component of my position vector. So each one only requires the power rule, 3t squared plus 8t, and 4t cubed minus 3t squared. And I want the velocity vector at t equals 1. So now that I have the velocity vector, I can substitute 1 into my t. So I'm going to end up with here 11. So it's going to be 3 times 1 plus 8 times 1. So I'm going to end up with 11. And then here I'm going to end up with 4 minus 3 if I'm plugging in 1. So my velocity vector at time 1 is 11, 1. So now let's move on to part B. Part B is asking me to find the speed of the particle at time t equals 1. So first I need the speed of this particular particle with this position vector valued function. So remember, speed is the absolute value of velocity. In this case we're talking about the vector velocity, so the absolute value means the norm. So our formula for this is going to be x prime of t squared plus y prime of t squared, and all of that underneath the square root. So this is the formula for speed. I don't know why I put y prime of 2. Sorry, it's y prime of t squared. And now I need to substitute 1 because I want the speed of the particle specifically at 1. So if I substitute in 1 here, well, x prime of t, we found right here, this was x prime of t. So if I substituted 1, well, I already did that in v of 1. So here, what I'm really doing is substituting in these two quantities into this one, x prime of t and y prime of t. So x prime of t, or x prime of 1, is 11 squared, and then plus y prime of t is plugging 1 in, which I've already done when I found the velocity vector at 1, so this is 1 squared. So this is the square root of 121 plus 1, so the square root of 122. And that's my answer for part B. And finally, for part C, I'm asked to find the acceleration vector at t equals 1. So that means I need to take the derivative of the velocity vector, which again is nice because it's only the power rule. So we're going to have 6t plus 8 and 12t squared minus 6t as my acceleration vector, but at 1, I need only substitute 1 into the t's. So here I'm going to get 6 plus 8, so I'll get 14, and then 12 minus 6, so I'll end up with 6. So hopefully a pretty straightforward first example. It's like those problems where you're given a position function and then asked to find the velocity at a particular point. So you take the derivative, plug in a number. Acceleration at a point, take the second derivative, plug in a number, and then speed is the absolute value of velocity. So it's just extending those concepts now to, instead of just functions, we're looking at vector valued functions. Alright, another example. An object moving along a curve in the xy plane has position x of t, y of t at time t, with dx dt equal to t sine t and dy dt equal to cosine of t squared. At time t equals 2, the object is at the position 1, 4. So this one's different because instead of being given the position vector valued function, I'm given the velocity vector valued function. So this is, remember, x prime of t, and this here is y prime of t. So that means that I've been given the horizontal and the vertical component of the vector valued function that is for velocity instead of for position as in the last problem. So let's keep that in mind. Find the acceleration vector for the particle at t equals 2. So what I'm going to do is write down what I have. I have v of t equals, and I'm going to choose to use the brackets, even though here we're given our information in parentheses. So just to remind ourselves, this is a vector. So v of t is t sine t and cosine of t squared. So for part A, if I want to find the acceleration vector for the particle at 2, that means I have to take the derivative of each piece independently just once more to get to acceleration. So for the first part, I do need to apply the product rule. So it's going to be the first times the derivative of the second plus the second function times the derivative of the first. So there's my horizontal component for my acceleration vector. And now I need to use the chain rule for the derivative of the second part. So the chain rule is going to give me negative 2t sine of t squared. So the derivative of cosine is negative sine, and then I need to take the derivative of the inside and multiply it. So there's my a of t, but I want a of 2, the acceleration vector at 2. So I'm just going to plug 2 in everywhere there's a t. So 2 cosine 2 plus sine 2. And then if I plug in a 2, I'm going to get negative 4 sine 4. And without a calculator, I'm just going to go ahead and leave my answer like this. So I can't evaluate this without a calculator. Now let's move on to part B. Write the equation of the tangent line to the curve at the point where t equals 2. So for part B, if I want an equation of a tangent line, I'm going to need a point and a slope. So I need the point specifically where t equals 2. So I need that xy coordinate point. Well, luckily for us, we know that at time 2, the object is at a position of 1, 4. So I have my point given as 1, 4. Whereas if I did not have this information, I would have to do a lot more work because I don't know x of t, y of t to substitute 2 into. But again, I'm given specifically at time 2, the coordinate points for x and y are 1 and 4. So there's my point, and now I need my slope, which means I need dy dx. So dy dx, I don't want to make that look like a t, so that's supposed to be an x, is going to end up being, well, if I have my equations given as dx dt and dy dt, remember that my formula for parametric equations, so that's ultimately what I've been given my parameter here is t, is going to lead me to dy dt over dx dt. So dy dt was cosine of t squared, and dx dt was t sine t. So I want the slope where t is 2. So if I want dy dx at t equals 2, now it's just substituting 2 into my slope formula. So I end up with cosine 4 and then 2 sine 2. So it's kind of an ugly slope, but it is the slope nonetheless. It's a numerical value. We're not going to plug it into our calculator. We're going to plug it into our formula, which is y minus y1, so my y1 is 4, equals m, so my m is my ugly looking slope, cosine 4, 2 sine 2, and then times x minus 1. So here is my equation of my tangent line. And there's no need to simplify. If this was a free response question, we leave it like this. If it's multiple choice, of course, we might have to do some rearranging to make it match one of the answers. Moving on to part C, find the speed of the object at t equals 2. So let's remember speed is the absolute value of velocity, but velocity is a vector. So that means I'm looking for the norm or the magnitude. And the formula for that is x prime of t squared. Well, x prime of t is dx dt. So we're looking at t sine t squared plus y prime of t, or dy dt. That's cosine t squared squared. And all of that's underneath the square root. And I want the speed at t equals 2. This is another one I'm not going to be able to solve without a calculator, so I'm going to leave my answer exact and just substitute in a 2 everywhere there's a t. So my answer is radical, the quantity 2 sine 2 squared plus cosine of 4 squared. So this is the speed of the object at time 2. So now let's move on to part D. Alright, in part D, we want to find the displacement of the particle from time 2 to time 7. So in general, if we remember, displacement is the integral of velocity. So here our velocity is a vector. So we're going to have to integrate each component individually from 2 to 7, and our answer will be a vector as well. So for part D, we're going to have a pretty big vector because I'm going to have 2 integrals for each component. So the integral from 2 to 7 of the horizontal component, so we have t sine t dt, and then the integral from 2 to 7 of cosine of t squared dt. And at this point, well, this first integral could be solved without a calculator. We could use the integration by parts. This one, we would not be able to solve this one by hand. So each one, we would solve each of these on our graphing calculator if we wanted the actual displacement as the vector to be numerical quantity. So here we have the integral set up, but we don't have the final answer. So I'm going to give you the final answer from the calculator. It is negative 6.361 if you truncate, and then 0.096 again if you truncate to the thousandths place. So now let's move on to part E. Find the distance of the particle from time 2 to time 7. So find the distance traveled by the particle from 2 to 7. So here, our distance formula is actually going to be arc length. So we're thinking about this particle that's traveling along a particular curve. So how far did the object travel? We're looking for the length of the arc. So in general, we're looking for the integral from 2 to 7 of the absolute value of v dt. So that stays the same when we're talking about distance, but now because v is a velocity vector, this is the integral from 2 to 7 of the magnitude, absolute value means magnitude, and it's going to end up being this portion here, right? So here's the absolute value of the vector v of t. It's this formula. So it's going to be t sine t squared plus cosine of t squared squared. So this is going to be my setup for finding the total distance traveled by the particle between time 2 and 7. So we would solve this on our calculator, and we'd end up with 13.229. So that is my total distance traveled from time 2 to time 7. And now we'll move on to part F, but we're going to definitely need some room. So for part F, I want to find the position of the particle at time t equals 7. Alright, so there was a formula for this, and basically we need to know, well, where was the particle at the beginning of an interval so I can figure out where it's at the end. Well, the interval that I'm concerned with, or that I've been using throughout the last 2 parts of this problem, is the interval from 2 to 7. And that works out for us because in the statement of the problem, I know exactly where the particle is at time 2. It's at 1, 4. So if I were to start my setup for the position of the particle at time 7, well, my starting location is 1, 4. So this is where I was at time t equals 2. So if I want to figure out where the particle is at time 7, I need to add to this location, 1, 4, I need to add the displacement of the particle during the time interval from 2 to 7. Well, I actually already did that. We did that in part D. So the displacement from 2 to 7 was done by each individual component and solving each of those definite integrals. So we got out that the displacement over that time frame was negative 6.361 and then 0.096. So that's what I'm adding to my starting location. So in general, my setup, so I will write it all out, is 1, 4 plus the integral from 2 to 7 of t sine t dt, and then the integral from 2 to 7 of cosine of t squared dt. So parentheses, the brackets, we're still talking about vectors here. So this is my starting vector is at 1, 4, and then this is my displacement of the particle still in vector form from 2 to 7, and we know this quantity again is negative 6.361 and 0.096, so we're adding those to the horizontal and vertical components of my starting location, starting meaning at time 2. So we're not talking about at time 0, but just starting as in over the interval of which I know my displacement. So if I add these two together, well, I'm really doing 1, 4 plus negative 6.361 and 0.096. And so when adding vectors, we add their individual components. So negative 5.361 and then 4.096. So this is where my particle is at time t equals 7. Alright, the last example, an object moving along a curve in the xy plane has position x of t, y of t, at time t is greater than or equal to 0, with dx dt equal to 2 sine of t squared, but dy dt is not explicitly given. We do know that at time t equals 2, the object is at position 3, 5. So in part A, we want to find the x-coordinate of the position of the object at time t equals 4. So we know the x-coordinate of the position at t equals 2 is 3, but we want to know, well, where is the object at time 4? But specifically, the x-coordinate of the object. Well, I have information regarding the rate of change of the x-coordinate. So remember, this is x prime of t is equal to 2 sine of t squared. So if I want to know about x, I'm going to need to integrate. And part A is actually an application of the fundamental theorem of calculus part 1. So here's what I'm setting up. I'm going to set up the integral from 2 to 4 of x prime of t dt. So let's talk about why I chose those limits of integration. Well, I need to know what's going on at 4, and I know what's going on at 2. So that's why I chose my limits of integration to be from 2 to 4. I chose to integrate because I need to go from velocity back to the position function. So that calculus operation is integration. And now I'm saying this is an application of the FTC part 1 because the integral from 2 to 4 of x prime of t dt, well, that is equivalent to, well, the antiderivative of x prime, that's just x of t from 2 to 4. So this is really equal to x of 4 minus x of 2. Whoops, parentheses went wrong there. So minus x of 2. And remember, I have x of 2. So this right here, that is considered to be x of 2. And that quantity is 3. So I can find this quantity. So I'm going to rewrite it as the integral from 2 to 4 x prime of t. That's 2 sine of t squared dt. So this equals x of 4. It's what I'm looking for. The position, the x value, the x location, the x coordinate of the position at time 4 minus x of 2, well, that is 3. So how do I solve for x of 4? I add 3 to the other side. So x of 4 is 3 plus the integral from 2 to 4 of 2 sine of t squared dt. And that evaluated is 2.884 if we truncate. So that is the x-coordinate of the position at time t equals 4. Now for part B, at time t equals 2, the value of dy dt is negative 6. Write an equation of the line tangent to the curve at the point x of 2, y of 2. So to find an equation of a tangent line, we need a point and a slope. So the point is x of 2, y of 2, which is actually given to us in the original statement. At time 2, where was the object? At a point 3, 5. So there's our coordinate point for part B. So our point that we need is 3, 5. And we're going to need dy dx at t equals 2. But dy dx is dy dt over dx dt. So I want each of these at t equals, at t equals 2. Sorry about that. So dy dt, although I don't have it explicitly, I do know that at t equals 2, dy dt is negative 6, which is good enough for me. So I know negative 6 is dy dt at t equals 2, and to find dx dt, I can substitute 2 into my formula. So I have 2 sine 4 as the denominator, so here's my slope. And I plug that into point slope form of a line, so y minus 5 equals negative 6 sine 4, and then x minus 3. So there's my equation of a tangent line to the curve, specifically at the point t equals 2, but I didn't need dy dt explicitly as long as I had that specific value that corresponded to t equals 2. For part C, find the magnitude of the velocity vector at time t equals 2. So the magnitude of the velocity vector is putting absolute value bars around this v of t. So let's remember that would be the square root of each component, so x prime of t squared plus y prime of t squared. And so I want this at t equals 2. So the absolute value, or the magnitude of the velocity vector at 2, and that's going to be the square root of x prime of 2 squared plus y prime of 2 squared. Well, y prime of 2 squared, that's dy dt at 2, which I was given in part B. So that means this quantity here is 6. And to find x prime of 2, well, I did that in the previous part as well, just substitute 2 into dx dt. So 2 sine 4 quantity squared, and then plus 6 squared. So the magnitude of the velocity vector, remember magnitude is like putting the absolute value bars around the vector, which is the formula, the square root of the horizontal component squared plus the vertical component squared. But we wanted to know what was going on specifically at 2, because we wouldn't be able to generalize this portion for y prime of t. We don't have dy dt. But we do have enough information at 2. We know that that quantity is negative 6, actually. Sorry about that. So that should have been a negative right there. But either way, it's the quantity is squared. So this is my magnitude at time t equals 2. And finally, part D. For times greater than or equal to 3, the line tangent to the curve x of t, y of t has a slope of 2t minus 1. Find the acceleration vector of the object at time t equals 4. So this one's kind of tricky. We're just going to write down what we have, what we know, and manipulate things until we can put our pieces together. So we want the acceleration vector. Let's start with that. So the acceleration vector, a of t, what I'm going to need is x double prime of t, y double prime of t. So where our concern lies is with y double prime of t, because we don't even have y prime of t. So the horizontal component, no problem. I can find that part right now. So let's just go ahead and do that. X double prime of t, well, this right here is already x prime of t, if you remember. So the derivative of this requires a chain rule. So it's going to end up being, well, the derivative of the inside is 2t, so I'm going to have 4t cosine of t squared. So there's my horizontal component of my acceleration vector. But now the problem is, well, what is y double prime of t if I don't even have y prime of t? But the other piece of information I'm given is that the line tangent to the curve, x of t, y of t, has a slope of 2t minus 1. So if I have the slope of a tangent line, what was really given to me right now in this expression is dy dx. So I was just given dy dx is 2t minus 1. So how does that help me though? How do I make the transition? How do I get to dy dt? Well, what do I know about dy dx? That's dy dt over dx dt. So this has to equal 2t minus 1. So again, what am I searching for? I'm searching for dy dt. Well, I know dx dt. I can make that replacement. So I'm going to go ahead and do that in a different color here. So I'm going to replace dx dt with what I know dx dt to be, 2 sine of t squared. So how am I going to isolate dy dt? I'm going to multiply both sides by 2 sine of t squared. So I just found my dy dt. Now this dy dt is only applicable for t values greater than 3, but that's okay because I want the acceleration at time t equals 4. So I'm going to go ahead and erase the denominator here of dy dt. So dy dt equals 2t minus 1 times 2 sine of t squared. So I do need to take the derivative of that because I want y double prime of t right now. So that means the second derivative with respect to t, well, that's going to require a product rule. So 2t minus 1, the derivative of this, so I should be careful, this needs parentheses, that's going to be our chain rule again. We just did that. So that one was 4t cosine of t squared, plus the second function, 2 sine of t squared, times the derivative of the first, which is just 2. So what goes right here is kind of a big messy thing. So 2t minus 1 times 4t cosine of t squared, and then plus 4 sine of t squared. So now all that's left to do is substitute in 4. So we wanted the acceleration vector at 4. So a of 4, we're just going to leave it pretty messy. We're not going to plug it into our calculator. So if I plug in 4 here, I'll get 16 cosine of 4 squared is 16. And then here, if I plug in 4, I will get 7. But then times this 4, I'm just going to leave it. A 7 times 16 cosine of 16 plus 4 sine of 16. So as messy as that is the acceleration vector of the object at time t equals 4.